Okay, let's do a quick check. How's the sound? You can hear, give me a thumbs up. All right. Okay, Royston, 那个 lesson 你看了吗？上次那个 already? Okay. Otherwise, you cannot catch up later. Okay, we'll start in a minute. Okay, so today I will finish up the gravitation. And next week we'll cover the moment and also the projectile, which will be coming out in your exam. I already received the exam tips. So that includes the projectile motion and moment, which we will cover after we finish this gravitation. Okay, so today I will finish up everything, and next 2 weeks will be the revision. Okay, so our lesson today is on satellite. Now, just a little bit of recap from last lessons. The natural motion of any object. Okay, now, by the way, if there's any lagging, let me know because my internet today is not very good. Okay, so now let's start. Now, the natural motion of any object is linear, is a straight line. A satellite orbiting Earth is moving in. Initially, okay, the natural motion would be in a straight line. Now, because now the way we label the velocity is tangent to the circumference of the circle, right? Okay, here we plot 2 points, point A, point B. When the satellite go from A to B, it is being pulled downwards by the gravitational force. Okay, now from here, it continues to move in straight line. And as it moves from this point to this point, again, it will be pulled downward. And it continues in this direction, straight line. Again, whenever it tries to exit, here, it will be pulled downward again. So this process repeats and you get an orbital motion. Okay, so this velocity, V1, V2, V3, V4, they are constant in value, but they are not the same because the direction is not the same. So it is always trying to go out. The satellite is always trying to go out, and the Earth is always trying to pull it. the V of the satellite is so large that it will not fall back into the Earth. So neither will it move towards the Earth, nor will it get away. Okay, so there is a balance between that. Now this balance, we can say that there's a force constantly pulling the satellite towards the Earth, and that force can be represented by mv square over r. Okay, force equals to mv square over r. So this itself is the force, this thing. This is the force. And it depends on the velocity, the radius. So these two already constant, right? It's fixed, right? Because the radius is the radius of the orbit. M is the mass of the object. So it depends on the velocity of the satellite. If the velocity of the satellite is the same as this force here, then it will keep on moving in perfect circle. Okay, now from here, we have already learned that gravitational force can be written as G mm, mass of Earth over m, r square equals to mass v square over r. Cancel, cancel, and then we get v equals to square root of gme over r. Now, this r is equals to r plus h. Okay, r plus h, meaning that the radius of the Earth plus the altitude of the satellite here, r plus h. So I can write this as v equals square root gme over r plus h bracket, like this. Okay, which formula you need to remember? This one. This is, let me mark this down, equation 1. Okay, now from here we can see what are the constant here. Constant gme, okay, gme and r are the constant. So only thing that affects the velocity of the satellite would be the height. This is very, very important information. So we can say that when the satellite is higher up, is at high altitude, it needs less velocity to orbit. Because if this is high, then the velocity will decrease, drop. 越高，它走到越慢。如果你的 satellite 越靠近那个地球的 surface 啊，它走到越快。Okay, so remember this. Now you can also prove it. You can prove it mathematically like this one, or you can prove it conceptually. Think of it like, if it's close to the Earth, then the force of attraction would be very large. Because the force is very large, so if the satellite want to keep in orbit, want to keep itself moving in orbit, then it has to move very fast to counter the strong gravitational force. Okay, conceptually, mathematically, we can say that whenever satellite is at high altitude, it needs less velocity. So I write here, it says that higher satellite need less velocity, and conversely, lower satellite need more velocity. Okay, huh? Okay, so this is what we talked about in the last lecture, right? So from here, now we get the relationship between the velocity of the satellite depending on the altitude, meaning that at here, this height, we can calculate what is the speed it is moving at. If I increase the height at this height, we can also calculate what is the speed that it is moving at. And eventually here also we can calculate the speed it is moving at. So here we get the relation between the velocity and height of the satellite. Now, what we want to know is the time period of the satellite. Okay, what is it? Time period. Okay, period. What is period? Period is, you remember last time I talked about period is defined as T capital, and it is the time taken for one revolution or one orbit. 它走一圈，它要多少时间? Okay, so if Earth move around the sun, it needs 24, not 24, sorry, 365 days. Okay, one orbit revolution around the sun, that's 1 year. Okay, that's the period. For the period of satellite, there are many types of satellite. There are satellites that has a period of 24 hours, the same as the Earth rotation. Later we will come to that. What is that satellite called? Okay, so understand period is the time taken for one revolution orbit. The unit, SI unit, is second. Okay, now you see, speed is equals to distance divided by time. And if I want to find the period, so I take time t period would be equals to distance divided by speed. And the distance traveled in one revolution, one orbit, would be 2 pi r. Again, this r is what? The radius of the Earth plus the altitude. Okay, the radius of the Earth plus altitude divided by v. Okay, v. So t 等于 2 pi r over v. This formula also you need to remember. Let me box this, especially for calculation. Okay, like this. Now from here, period, we know that from our previous formula, v equals to square root gme over r, right? We can put in the formula. Okay, so if you put in the formula, t 等于 2 pi r divided by square root gme over r. Do a little bit of simplification. 2 pi, okay, times r divided by gme over r. So t would be equals to 2 pi times r square root r divided by square root gme. Until here, what happens to this? R 跟 square root r 我把它放进那个 square root。OK， 所以我拿到这样子 ，t 等于2 pi 乘这个 r， 我把它放进这样子啊 ，square root r 乘 r square divided by square root gme。OK， 一样嘛，因为这个一 square root 过后你搬出去就等于 r， 你放进去，然后这里就变成 t 等于2 pi 乘以 square root r sun divided by gme. Again, this one, please take note. This formula, also you're going to need this. Especially when do you need this? You need this when there's a relation between period, mass, and the orbital radius. What is the orbital radius? The r is the orbital radius, the radius of the orbit, and it is r plus h. Okay, so what are the constants? This is constant, g constant, me constant, pi constant. 只有一个东西会 affect r sun， 这个 orbital radius 会 affect 你的 period。意思是说，如果你的 calculate 你的 satellite 很靠近地球的话，它的 orbital radius 小的话，它的 period 会什么？它的 period 会 this one. If this is small, period will be also small. Okay. If it's big, then if it's very far away, then the period will also be very big. So the time taken for the satellite to make one round would be very long. So the bigger the orbit, the longer it takes for one round to make one revolution. Okay, and you can calculate, no problem. You can use this equation to calculate. Okay, now from here, this formula is the relation of V and H. This formula is the relation of time and H. The time is in period. Okay, time and the altitude H. Okay, now using this formula, let's say if we want to send a satellite into orbit, and I want the satellite to go around the Earth 24 hours, one revolution. Okay, so I want the period to be 24 hours. At what altitude should I put it? At what altitude? We can calculate. So from here, t equals to 2 pi square root r cube over GME. Okay, period is 24 hours, right? So we'll put 24 hours times 60 into minute and times 60 into second. Okay, equals to 2 pi square root and then r cube. Gravitational constant 6.67乘10减11乘以 mass of Earth is given 5.97 times 10^24 here. Okay, then calculate. Okay, this one, if you solve this, you will get r cube equals to 7.53 times 10 power of 22 meter, and then r equals to 4.22 times 10 power of 7 meter. What is this r again? This r is measured from the center of the Earth, right? 所以如果我要知道它的 altitude 啊，这个是它的 answer 吗？不是啊，我要把它减掉 Earth 的 radius。OK， 因为 r 是等于 Earth radius 加它的 altitude， 所以 altitude equals to this minus the Earth radius. So 4.22 times 10 power of 7 minus out the Earth radius, which is 6400. This is in kilometer. So change it to meter is 3 more zeros. 你拿到什么？你拿到 approximately 36,000 kilometer. This is the altitude of the satellite at 36,000 meter. Is it high? It's very high, right? The radius of the Earth is 6400 kilometer. This is 36,000. Okay, so this value is very, very significant compared to the radius of the Earth. So at this height, the G definitely will be a different value. Okay, so if I want my satellite to orbit 24 hours one round, same as the rotation of the Earth, I have to send the satellite at 36,000 kilometers above the Earth's surface. And this satellite has the same period as our Earth. Same period as Earth. What is this satellite called? A satellite that has the same period as Earth, we call it geostationary. Geostationary satellite. Okay, so if the question asks you, what is geostationary satellite? A satellite that has the same period as the period of Earth. As the same period as the period of rotation of the Earth. 24 hours. 24 hours. Now, this formula, guys, be careful of this formula. So here's something I want to stress. T equals to 2 pi square root r cube over GME. 这个 formula 不一定这个 mass 是 Earth。OK， 这个 mass 是那个 central object 对吗？在这个情况下啦，这个是地球的重量啊。然后这个 T 是 satellite 的 period。satellite 的 period， 这个 R 就是它的 radius of orbit 啦。In other words, I can say that the T, this one is the orbiting object. Orbiting object. And this is the central object. Central object. You got two objects, right? Earth at the center, satellite orbiting around it. So the T, you are calculating the T for what? You are calculating the T for the satellite, not the Earth. The orbiting object. And the M is the mass of the central object. Remember this. R is measured from the center. Why is this important? Because if I ask, like Jupiter, this is Jupiter, and I want you to calculate the period of Jupiter's moon. Jupiter's moon orbit around Jupiter. So in this case, I would use the same formula. The T would be the period of the moon, and then the M would be the mass of Jupiter. Okay, using the same formula, ME would be the central object mass of Jupiter, satellite is T. Or I can use it to calculate the period of the Earth orbiting around the Sun. In that case, the Sun would be the central object. And using this formula, the answer for the T would be the period of the Earth. Okay, so it depends on the context. It depends on the context. It is not always ME, no. Okay, using the same formula, you can also 你可以 terbalik 找它什么？找它的 mass， 找那个 central object 的 mass。Okay， 比如说 question 问你 calculate the mass of the sun if the Earth radius and orbital period is blah blah blah. Then you just put in the value using the same exact formula. You got the T, you got the R of the Earth. 你调转找回你的 central object 的 mass M. That's why this formula is very, very important and you need to take note. Okay, so what formula we have? This one, so far the first one, and then the second one, this one, orbital period. Okay, just some technical names. T stands for orbital period. The R stands for orbital radius. Orbital radius, the radius of the orbit. Okay, orbital, or sometimes you will see mean distance. It says mean distance between satellite and the Earth. OK， 接下来我们看什么是 geostationary satellite。Geostationary satellite, as the name suggests, geo means the Earth. Stationary means at rest, right? Geostationary satellite means that the satellite is at rest with respect to the observer on the Earth. Okay, what does that mean? Right, see, this is the Earth. Suppose that I stand here. You stand here. This is your current position. You look up to the sky, you see the satellite is on top of you. Okay, now this satellite, what is the period of the satellite? The period of the satellite is 24 hours. So when it makes one round, that takes 24 hours. Okay, same as the rotation of the Earth. Now, what is this height again? Just now we calculated the height, right? The height of this satellite has to be exactly 35800 kilometer. Just now we calculated approximately 36000 km, right? 36,000 km. That is the altitude for geostationary satellite. If you want to get the period exactly equals to 24 hours, you have to be as accurate as possible to the altitude. Now, from here, when 6 hours has passed, okay, after 6 hours, now my position is here. Okay, 6 hours. The satellite also, after 6 hours, it has gone here. This is also 6 hours. Same period, right? When I look up after 6 hours, I look into the sky, I see the satellite is still there. It's directly above me. Another 6 hours passed. Now I'm here, and the satellite also is here. When I look up, I see the same satellite, as if it has not moved at all. Okay, again, 6 hours again. Now my position is here. The satellite is gone from here to here. Okay, 3/4 of the revolution, 3 quadrant. Again, I look up, I see the same satellite, same position. And here, everywhere I go, the satellite follows me. What is the advantage of this? Why do we want a geostationary satellite? Everywhere I go, I see the same satellite just above me. So the satellite is stationary with respect to me, to my location, to my geological location. That's why we call it geostationary. Okay, it is always pointing at the same geological location. What is the advantage of geostationary satellite? The advantage of geostationary satellite is that if we want to communicate with the satellite, for example, I want to send data or I want to receive data, okay? I don't have to change the direction of my antenna. This is the antenna. I fix my antenna directly pointing to the satellite. This is the axis of the antenna. The axis directly pointing towards the satellite. When the antenna rotates, because the Earth rotates, the satellite will also follow suit. So these axes remain the same everywhere. Okay, it's like this. This is the antenna. Satellite is pointing up. When this moves to the side like this, satellite is also follows the axis. So no matter where it goes, the satellite will always be in the same axis as the antenna. So we don't need to change the position or change the antenna. We fix it, and then it's always aligned with the satellite. Okay, so what are the applications of the geostationary satellites? This is one of the advantage. Okay, where do we use it? We use it for our GPS. Your GPS satellite? Yes, it is a geostationary satellite. Your TV satellite, it is a geostationary satellite. Your Wi-Fi, internet, not Wi-Fi, sorry, internet. Internet or any form of data transmission uses, all of this uses geostationary. Okay, now where do we place it? Geostationary 我们放它在外面哦，你知道它的 altitude 了，你知道它的 period 了，这样我们要放在哪里？放在哪里呢？我们是放在它的地球的 equator 的上面。OK， now 这个是你的，这个是地球。We all know that the Earth, the axis of rotation of the Earth is slightly tilted. It's not straight, right? It's slightly tilted to one side, like this. Okay, so this is the axis of rotation. The equator of the Earth, somewhere here. Where do we put the geostationary satellite? We put it above the equator that shares the same axis of rotation. Now, where? You see, this is the equator, right? This is the center of the Earth. If I draw the equator plane, the equatorial plane, like this. Imagine in 3D. Okay, wait. Extend these lines. Okay, this is the plane. If you can understand my drawing. This one is the plane. Okay, so this is the equatorial plane. In other words, it's the plane of the equator. You just imagine the equator and then you extend it outward. Okay, extend it outward. So we put the satellite on the equatorial plane. So that, why we put here? If we put here, so that this satellite will share the same axis of rotation with the Earth. Okay, so you cannot only make, not only you make the period the same, also you have to make sure the rotation is the same. Otherwise, it will be rotating to this side and the Earth goes to that side. Okay, so this one, how do we describe the location of this satellite? We said that we put it here. Okay, where is it located? It is located exactly. We said radially, okay, radially above equator. And it has the same axis of rotation that of Earth. Okay, so that's for geostationary. Now, another word for geostationary is geosynchronous. Sometimes you will see these words geosynchronous. It actually is very, very similar to geostationary, but they're not exactly the same. The only difference is geosynchronous satellite, the location is slightly tilted to one side. Okay, for example, like this is the orbit of the geostationary, right? Okay, so this is geostationary. Geostationary. Geosynchronous will be slightly tilted like this. Okay, put here. This one is other one. Geosynchronous, NOUS satellite. Both satellites, they have the same period, 24 hours. Okay, one revolution, 24 hours. This one also, one revolution, 24 hours. But geosynchronized takes a different path. Okay, so as a result, if you look at the path of the you look from the Earth, if you look to the sky, you see the path of the geosynchronous satellite, right? It's going like curve a bit like this, and then like this, like a curvy shapes. They have a name for this shape. I forgot what they call it, the name already. Okay, because of the axis is a bit different. Okay, but the period is the same. For geostationary, is exactly the same. When you look into the sky, it's the same position everywhere. Okay, regardless of your location, it's the same. Okay, so that is for satellites. Okay, now I'm going to create a new meeting and we will continue from there. The next part is the last part. I want to finish up the escape velocity, the escape velocity, and then we'll do some practices. Let me create new meeting.